In this lecture, I'm going to review imaging performance and look at some objective measures of performance, and I'm also just going to review the various different limitations that there are on what ultrasound can do that we've spoken about before. It's quite possible to say, I like the images from this machine better than the images from that machine, and for that to be a purely subjective impression. But in order to talk more objectively about image quality, you need to talk about several different aspects. And doing this does help you to know what to do in order to maximize image quality. So we'll look at 3 different measures of image quality. The first of those, spatial resolution, is related to the clarity and sharpness of the image. Now, there's a formal definition of spatial resolution, which is the minimum separation between 2 objects that are required for those 2 objects to be seen as separate. And when we do see the 2 objects as separate in the image, we say that they have been resolved. So it's the minimum spacing needed for 2 objects to be resolved in the image. In ultrasound, we traditionally talk about 2 different aspects of spatial resolution: axial, which means resolution in depth, and lateral. And the reason for this is that they are determined by different parameters of the machine, and therefore they can be optimized separately. Also, we want to know their relative magnitude. There's a term, contrast resolution, and this is used to talk about your ability to see small variations in the echogenicity of soft tissue. So the typical situation would be if you were looking in the liver to see if there was abnormal tissue. And then finally we have temporal resolution, which of course relates to time. So I'll start by looking at axial resolution, which remember is resolution in depth. Imagine we have 2 different objects at slightly different depths, one of them at a depth D1 and the other one depth D2. Let's look at the echoes. The echo from the more superficial tissue arrives at time T1 after the transmit pulse, and then the second echo arrives a bit later at time T2. I'm also showing the duration of the transmit pulse, which of course is equal to the duration of the echoes, and I've labelled that tau. If these 2 objects are to be seen as separate in the image, there must be some clear space between them, which means that these echoes must not overlap. So we can see that the minimum separation between the echoes is simply the pulse duration tau. As long as the 2 echoes are separated by more than that, then there will be clear space between them. They'll be seen as separate in the image. When we translate that back to the depth, we find this means that the axial resolution is simply propagation speed times the pulse duration divided by 2. So axial resolution is determined entirely by pulse duration. This doesn't vary, so the axial resolution is the same at all depths. Lateral resolution, we'll see, relates to beam width and therefore varies with depth. How do we maximize the axial resolution? By using high frequencies. Lateral resolution refers to 2 objects at the same depth, separated by an amount x. As the beam scans from left to right, it's going to smear out each one of these objects in the image by an amount equal to the beam width w. And so in the right-hand side, I'm showing the sort of thing we would see in the image, that each of those dots is being imaged as a line of width w. It's fairly easy to show that as long as this separation x is larger than the beam width, there will be clear space between these 2. They'll be seen as 2 separate objects. And so the lateral resolution is very simply the beam width. Getting the best possible lateral resolution involves focusing and using as high a frequency as possible. This is a table taken from my textbook. I just wanted to show you some typical numbers. This has been calculated for a 6 MHz probe operating at a focal depth of 4 centimeters, and the values are calculated at focus. The axial resolution is about 0.4 of a millimeter, which is very good. The lateral resolution is about 1¼ millimeters. And then for completeness, I've also calculated the slice thickness, and this is 4.2 millimeters. So you can see that the lateral resolution is worse than the axial resolution by about a factor of 3, and then the slice thickness is worse than the lateral resolution, again by about a factor of 3. So the axial resolution is by far the best resolution, and this is why you are always urged to use perpendicular incidence whenever you can to get clear images of tissues and to make accurate measurements. Now let's look at contrast resolution. Just to remind you, this is a measure of your ability to see small variations in the echogenicity of soft tissue. The main issue here is image artifacts. So image artifacts cause echoes to be shown in the image which do not directly relate to the anatomy. So essentially, the artifact echoes are going to muddy the image and make it harder for you to see small variations in echogenicity. Now, by artifacts, I'm talking about things like speckle, a reverberation artifact, slice thickness artifact, and so on. To get the best contrast resolution, you need the cleanest image with the least amount of artifact. This involves several different things. Most importantly, it requires good scanning skills. With experience, you'll learn to find the best window to image a particular area, and you'll learn how to apply the right amount of pressure and whether you should have the probe perpendicular to the skin surface or angled. There are also technical things that reduce artifacts, so the use of harmonics, compound imaging, frame averaging. All of these things reduce artifacts and therefore improve contrast resolution. The other thing I mentioned here is matrix probes, which I showed earlier. While they're much more complex and therefore more expensive, they do reduce slice thickness, and therefore that will reduce one particular source of artifact echoes. There's one other thing you can do to maximize the contrast resolution, and that's to make sure that you've optimized your imaging settings. So make sure that the overall gain, the TGC, your choice of frequency, etc., are the optimum for the particular application. Now let's look at temporal resolution. The main thing here is the frame rate, and I've talked about frame rate at various times in previous lectures. You should remember that frame rate is very much dependent on penetration depth. When you're scanning very deep, the machine has to wait a long time for the echoes to come back from that depth, and this slows down the imaging rate and therefore slows down the frame rate. The other factors that are important are the number of lines in the image and also the number of pulses that each one of those lines requires. Many machines, not all, but certainly the more top-end machines, have the capability of producing several beams simultaneously and therefore gathering the echo information more rapidly, and a typical number would be 4. So the machine would be able to speed up its imaging rate by a factor of 4 by acquiring echoes for 4 different beams simultaneously. You can do something else to also increase the frame rate, and that is you can reduce the number of lines needed to make each image. The way to do this is to reduce the width of the image. With at least some probes, you can generally reduce the field of view, and this will automatically reduce the number of lines and therefore speed up the imaging rate. The other thing that you can do, of course, is to turn off optional modes like harmonics, compound scanning, multiple focus, etc., and color Doppler I should mention as well, because all of these slow down the imaging rate. So if they're not absolutely essential, turn those extra modes off and the frame rate will increase markedly. Now, the other thing that I should mention about increasing the frame rate is that using right zoom, which I described to you before, you reduce the area being scanned very significantly, and that's going to increase the frame rate. There is one other factor that also affects the temporal resolution, and that's frame averaging. I've mentioned before, this is used to reduce speckle. It involves averaging the information from the newest image with the previous image. And of course, if there's been motion so that objects have moved between one image and the next, they'll be blurred when you do this. Obviously, when you want the best possible temporal resolution, frame averaging should be turned off. Here we have a curved array image of the liver and a kidney, and you can see that we have a single focal depth and we have a frame rate of 28 frames per second. On the right, I'm showing what happens when I turn on an additional focus. So we're now using two different focal depths, and the frame rate has approximately halved. Now let's suppose I wanted to keep the two focuses, but I also wanted to increase the frame rate. Now here in the second image, I have reduced the field of view. I've narrowed down the image, and now the frame rate has increased to 27 frames per second. Here, I've increased the frame rate even more by narrowing down the field of view even more. And obviously, if I did zoom the image and selected a relatively small area, that would have a similar effect. So this is one easy way that you can have an impact on the frame rate. So now in this one slide, I'm just going to review the various important limitations on what ultrasound can do. The ultrasound frequency limits the spatial resolution. Spatial resolution, of course, then very significantly can affect measurement accuracy. Frequency also affects penetration. As you increase the frequency, the penetration decreases. You may remember that the product of frequency and penetration is constant. So if I was to double the frequency, I would halve the penetration. So basically, we have a conflict between penetration and resolution. To improve the penetration, we need lower frequencies. To improve the resolution, we need higher frequencies. And so always the frequency you use will be the best compromise between the penetration and getting the best resolution possible. Attenuation in normal tissue limits the depth of penetration. When you have abnormally high attenuation in some region, then you can get shadowing. If you have unusually low attenuation, then you can get enhancement. At the extreme, when you have things like gas and bone, you get essentially complete reflection and scattering of the ultrasound, and therefore virtually no energy at all travels beyond that point, and therefore you lose the ability to see deeper tissues entirely. The propagation speed, of course, comes into determining the frame rate, and the propagation speed is simply a physical constant. And then finally, I've talked about image artifacts and the fact that they reduce image quality. Of course, they can also introduce uncertainty and confusion sometimes. Artifacts also limit the contrast resolution, and they also tend to degrade the accuracy of measurements. In addition, as I've said, artifacts can sometimes block imaging. So that may be severe shadowing by a fairly large object, or it may be something like a massive gas bubbles causing a large area of ring down and making it completely impossible to see the deeper tissues. So all of these things limit what ultrasound can do. One of your skills is to know how to weave your way through these to get the best possible image quality. So in summary, we've looked at spatial resolution, and we find it's quite simple that the higher the frequency is, the better the resolution will be. We also saw that the axial resolution is better than the lateral, And this means that whenever possible, you will seek to image tissues at 90 degrees. We saw the contrast resolution is optimized by minimizing artifacts and by making sure that your imaging settings and controls are set to the optimum values. Temporal resolution largely depends on frame rate, and the best way to improve it is to reduce the field of view or to use zoom and to turn off unnecessary additional operating modes so that you go back to just standard basic imaging. And then, of course, I've just reviewed those limitations.